All right, so we pretty much finished up our conversation about electrophilic aromatic substitution, and we want to talk in more detail about a reaction that was actually brought up on Monday. What happens if you have a nucleophile reacting with an aromatic ring? Usually, an aromatic ring is not electrophilic. Most nucleophiles are not going to be strong enough to attack the ring. And the reason for that is because if a nucleophile attacks the ring, one, there's no leaving group. And so the only thing that could happen is during that attack, to avoid a 5-bonded carbon here, which would be impossible, the pi electrons would have to swing away out onto a carbon. And even though there'd be resonance to stabilize that, those pi electrons would sit in a p orbital that would overlap with the adjacent p orbitals. The ring would no longer be aromatic, and the negative charge, even spread out over multiple carbons, a negative charge on a carbon is something that's quite unstable. So that usually won't occur. That doesn't mean there's no way for a nucleophile to ever attack an aromatic ring. It just means that we need specific criteria to be met, or we need a specific scenario where that can occur and stabilize the resulting negative charge instead of it being on a carbon or multiple carbons through resonance, which is still relatively unstable. So, one nucleophile that you could think about using would be an OH minus. An OH minus is a pretty strong nucleophile. It's nice and small, doesn't have too much sterics, it's got a full negative, so it's really ready to start sharing a pair of electrons. And to do so, it could attack the ring. If we wanted to attack, we would probably expect it to attack a carbon where there's a leaving group. And obviously there is a leaving group here, and it is the bromine. One thing we can't do, though, we've talked about this, is to have the nucleophile attack that carbon and push the bromine out in the same step. If I were thinking about an SN2, that would require the nucleophile to attack from the back side from where the leaving group is. And since this is flat and all these atoms, nuclei, are in the same plane, that would actually require the nucleophile to attack through the ring the back side of where the bromine is. And since this is an sp2 hybridized carbon, the orbital overlap isn't properly aligned there, and the sterics associated with that ring would prevent the hydroxide from attacking. So we can't do that either. So what we're going to be looking at here instead is what conditions need to be met and how does this process work. So one thing about this is the ring needs to have some quantity of partial positive to attract the negative charge of the nucleophile. And that's why we need this nitro group here. Without the nitro group, this reaction is not going to work very effectively. It would require a much higher temperature. But 70 degrees is reasonable. Once I get over like 100, well, not 100, but once I'm over like 200 degrees to 300 degrees, at those extremely high temperatures, I start to risk collisions that are strong enough to just start breaking the molecule down and decomposing it. So generally in a research lab or in a synthesis, you wouldn't want to reach extremely high temperatures because your molecules start falling apart. So 70 degrees is definitely moderate temperature, and it shouldn't cause any really serious side reactions or decomposition of the structure. But the only reason that we can get away with this relatively low temperature is because of the nitro group, right? So just to remind you, last time we talked about a nitro group and what it looks like. And a nitro group has two oxygens on the nitrogen, one double bond, one single bond, positive and a negative. So strongly through induction, because the nitrogen is positive and more electronegative than carbon anyway, it will attract these electrons and put a nice big partial positive there, which can attract some electrons and put some partial positive here. Induction only extends one or two atoms away. But as we said on Monday, there's also resonance. This pair of electrons can shift to the oxygen, making the nitrogen even more positive, which would cause it to attract electrons from the ring, putting a big positive here. These electrons could shift over in response, putting a positive here, and these electrons could shift over, putting more positive here. So there are actually multiple carbons in the ring that have a lot of positive. And specifically, when the nitro is ortho or para to the leaving group, that creates a situation where the resonance involved in the nitro pulls electrons away from the carbon that the leaving group's attached to, and that's a key thing. That is going to create some partial positive there to attract in the nucleophile. So that is criteria 1. The ring must be electron poor. That creates a partial positive to attract the nucleophile. The ring must be substituted with a strong electron withdrawing group like a nitro group. That's the most common one. It's common because nitro groups are easy to install on the ring through a nitration reaction. There must be a good leaving group for the nucleophile to replace. And thirdly, the leaving group must be positioned ortho or para to the electron withdrawing group. Right, so we just explained that, and we'll see more of that in the next few slides, but just to reiterate, when the nitro group is placed, in this case para, or if it were ortho, its ability to withdraw electrons through resonance specifically places a partial positive on the carbon that we want the nucleophile to attack. So we need those conditions to be met. We need a leaving group, we need an electron withdrawing group to make partial positive on the ring, and specifically we need an electron withdrawing group that will withdraw electrons through resonance to put a large partial positive at the site where we want the nucleophile to attack. We really need to entice it in there, because otherwise the ring is not going to have enough positive to attract in a nucleophile. So here's an example. Here we just have a chloride instead of a bromide, basically the same thing. It's a good leaving group. So the mechanism here is going to involve the nucleophile attacking. And as we said, it can't come in from the backside because it's blocked by both sterics, and the orbital overlap isn't going to work out on an sp2 like it would on an sp3. So we can't do SN2. We can't do that on an sp2 hybridized carbon. So the only option is for the oxygen to come in here and push the pi electrons onto this carbon, and so this is where they would result. All right, so we're avoiding a 5-bonded carbon here by having the oxygen come in and form a new bond and pushing what were pi electrons here onto the carbon. Once they're there in a p orbital, they're in resonance with these other pi bonds, so they can shift in here and push this pi bond out there. So that would create a structure that looks like this. These electrons would swing in, making a pi bond here. These would swing out to become a lone pair here. And this pi bond would still be here. There's another resonance contributor where these electrons could come in here and push these here. All right, I can't push them in here, obviously, because that would make a 5-bonded carbon. All right, we can't do that. It's prohibitively unstable. And so that would make my structure look like this. So there are 3 resonance contributors here, but I don't want to forget the resonance contributor where the electron pair can shift here and push these out to the oxygen, because putting the negative on the oxygen is even more stable than having it on these carbons. So there's another resonance contributor that would look like this. Oh, it's already right here. Here the negative is on the oxygen, right? So this one resulted from this pattern where the electrons move out here to form a double bond between the carbon and the nitrogen and shift to the oxygen. So that's where we get the double bond there and the negative on the oxygen. So this is actually relatively stable. I've got negative, positive, negative, opposite charges next to one another attracting. I've got my negatives on the more electronegative oxygen atoms rather than carbon. And so this intermediate isn't terribly unstable, and its existence is really what allows this reaction to occur without needing an extremely high temperature to reach these really high energy transition states. So instead of a sigma complex, this is called a Meisenheimer complex. It's kind of a fun word. And then the last step re-aromatizes. In the EAS, we talked about most recently, the re-aromatization occurred where a carbocation would be stabilized by picking off a proton. Some kind of base, whatever the best base around is, would pick off that proton and push those electrons in to re-aromatize. So in the nucleophilic aromatic substitution rather than electrophilic aromatic substitution, everything's kind of the opposite. Right? In the EAS, we had the ring attacking electrophile. Here we have a nucleophile attacking the ring. And the ring becomes negatively charged instead of positive. So here, instead of picking off a proton to re-aromatize, we need to push out the leaving group. So these electrons would all swing back in here, re-aromatizing the ring, right? This pair here would end up here. This pair would swing down and end up here. This pair would swing in and end up here. And that finishes or re-aromatizes the aromatic ring there. And upon doing that, pushes the leaving group out so we don't make a fine bonded carbon. And so we've, in essence, the overall reaction here, whether we have a chloride or a bromine doesn't really matter, is we're starting with a pretty unstable negative on an oxygen and producing a negatively charged bromine. So thermodynamically, this process is quite favored. Going from a relatively unstable negative to a much more stable, larger negative that doesn't create as much of a charge imbalance in the terms of the positive to negative charge ratio is something that's favored. So thermodynamically, quite product favored. Kinetically, it's a bit tricky, which is why we need this heat. Right? Because even though this first intermediate has a lot of resonance stabilization, many of the contributors have a negative on a carbon, and that's a pretty unstable situation. If you put the electron withdrawing group meta to the leaving group and try to do the same exact reaction with the same exact conditions, you don't get any product. All right, so let's just look at that really quick. So if my leaving group is here, and my nitro group is meta to that, and if I ask you to show this mechanism, you'd want to draw out the nitro group like this rather than just showing it as NO2 because it gets involved in the resonance. In this case, it wouldn't be able to, which is the point we're making. So if the hydroxide attacks where the leaving group is, it can't push it out right away. It would have to push these electrons here. Oops, that wouldn't be resonance. That would produce the structure here. The negative on a carbon. Then these electrons could swing in and push these here. Oops. It shouldn't be there. It should be a pair of electrons. The nitro group is here. Then those can swing in here, but then to avoid a 5-bonded carbon, this pair would have to swing up here. So that there's no way to extend the resonance stabilization of this negative charge onto the nitro group like we saw in the last example. And so that's the point here. In this case, the only atoms that are helping to stabilize that negative are the carbon atoms. That would produce a negative there in addition, and the nitro group would be there. So the nitro group can't help to stabilize that negative. That makes a huge difference in how stable it is during the intermediate and during the transition state where the OH is attacking. And so we can't get up to this much higher energy, less stable structure with the same amount of energy that we could get to the more stable structure. So we need the nitro group to be ortho or para to the leaving group. Just to point out why the H3O plus is necessary here, since we'd typically be using excess NaOH to help drive this forward thermodynamically and kinetically to help aid in more frequent collisions. And when the hydroxide comes in here, the more of that we have around, the more often it's going to collide and go through the mechanism we just described. When that reaction is complete, we get this structure. But since there's still excess hydroxide around, which is a relatively unstable negative, it's going to deprotonate this. And that proton transfer is very product favored, because once the proton is transferred to the OH to make water, and the oxygen on the ring is now the negative charge, that negative can be stabilized with the carbons through resonance. So a resonance stabilized negative, even if the other contributors involved in negative on a carbon, is going to be more stable than this OH that can't be stabilized through resonance. So after the reaction produces the product, the excess OH minus will pick a proton off of that product. And really what you end up with is a negative charge there. So the purpose of the H3O plus in a second separate step, we obviously don't want to have the H3O plus with the NaOH, they'll just react together. The purpose of adding that in a second step is to provide a proton for that oxygen to pick up. So if we just wanted to complete the mechanism there, we'd have that oxygen pick up that proton to make an OH. Otherwise, we'd be left with the negative charge there. As we were saying, without the presence of the strong electron withdrawing group that really helps to stabilize the transition state, with mild heating, there's no reaction. I can get this to work though if I get the temperature up really high. This is a very high temperature to get this process to work. At that temperature, if my ring is even much more complicated than this, or even this structure here, I might start to see a decomposition of the molecules if they react too long. So anytime I increase temperature too high, I run the risk of providing the activation energy for side reactions that I'm not interested in occurring. So this might work. The yield might be limited if some of the reactants start to break down, and this, under these conditions, it's probably not the type of thing where I can just set it up and let it go for an overnight, because that energy might cause a bunch of side reactions to occur. And the practical ability to create this temperature is tough as well, because typically one of these substances is going to have a lower boiling point, and it's hard to get the temperature up above a boiling point because the substance will just vaporize and evaporate out of there. And even under reflux, you can't get the temperature much above the boiling point of the sample, because it just keeps boiling it away and turning into a vapor, transporting that energy away. So this is a serious limitation, even though on paper it works. I can do this more readily with a stronger nucleophile. So we know OH minus is a pretty strong nucleophile, but since oxygen has so many protons in its nucleus compared to most of the other second energy level atoms, it stabilizes a negative charge fairly well, right? We think of it as being a strong base or strong nucleophile because it's unstable. But there are negatives that are even more unstable. And so since it's hard to get the oxygen to come in here and do this reaction, because kinetically the transition state is quite high in energy, and OH minus, while being unstable, is not super unstable. And so to get up there, it takes a really high temperature. If I start with a nucleophile that's even less stable, like a negative charge on a nitrogen, that's going to start off higher in energy, so it won't require as high a temperature to get to the transition state where the negative is spread out on the carbons through resonance. So with a stronger nucleophile, I can get this to attack and go through that mechanism and push out the leaving group. So why is this stronger as a nucleophile than the OH minus? Why is the negative, basically what we're asking here is, why is the negative on the nitrogen less stable than a negative on an oxygen? And that just has to do with the number of protons. So the number of protons there is the key. Nitrogen has 7 protons, oxygen has 8 protons. So the extra proton just helps to pull those extra electrons in and stabilize a negative better than on a nitrogen. And we can also look up the pKa values of their conjugate acids to show that the NH2 minus is much less stable and much more reactive. And so it helps to get the process started kinetically since it's starting higher in energy. It also makes the process more favorable thermodynamically, right? Because if I'm looking at thermodynamics, I'm comparing the initial energy with the final energy after the mechanism occurs. Where's the final energy? Well, the chloride leaving group is really quite stable as a negative, so the final energy would be much lower. But if I'm looking at the negative delta G resulting from a higher energy reactant versus still a negative delta G for the OH, it's just a more negative delta G, so it's going to be even more product favored when I start with a less stable reactant. So here's a reaction that you can do, basically what we were just talking about. If you take this unstable, negatively charged nitrogen and have it attack, you would expect it to be positioned, if it goes through the mechanism we just described, where the electrons move to the carbon and they're stabilized through resonance, and then they shift back in and push out the chlorine. This reaction should only work through that mechanism if the nucleophile attacks the same carbon the chlorine's connected to. And so it should always end up at that position. But if you do this reaction in real life, what you get is an additional product here. And these are both formed in significant amounts. This one might be major, but it's not like I'm getting like 99% of this and 1% of this. These are both significant products, and the question then is, how does this even form? Because the mechanism we just looked at would require the nucleophile to attack the same carbon the leaving group's connected to. Right? So just to point that out, when the nucleophile attacks, and these electrons shift to that carbon, there'd be a methyl group down here. So the negative charge here would be stabilized through resonance, but eventually it would swing back in and push out the leaving group to re-aromatize the ring, and that would require the NH2 to end up connected para with respect to that pre-existing methyl group that was there. I mean, we can't even imagine how would the nitrogen be able to even attack this other group, or the other carbon. If it attacked there, how would the chloride get pushed out? So that's a mystery if you're only imagining the mechanism we just previously discussed. So there's an alternative mechanism that's at play when you use a strong nucleophile if there's no electron withdrawing group. Right? So I want to point that out. The mechanism we described back here worked specifically because there was a strong electron withdrawing group, ortho or para, to the leaving group. And when we set that up with the strong electron withdrawing group, para to the leaving group, we were able to show how the mechanism was facilitated by the extra resonance contributor where the negative exists on the oxygen rather than the carbon. If you don't have that electron withdrawing group and you just have a ring with the leaving group, you end up with, and a strong nucleophile, you end up with a different mechanism from the one we discussed. And this mechanism can be elucidated with carbon isotopic labeling, or you could just put the methyl group on there, which I think probably makes more sense. So rather than describe the labeling, let's just imagine there's a methyl group here. And I'll just draw this one a little bit differently. Actually, let me redraw that. So if there's a methyl group here, it would be here still in the product where the nucleophile replaces the chloride on the same carbon. And then the other product would form from the nitrogen attacking a different carbon. So how do we get this product? That's what we're kind of talking about. So what happens here is, put this methyl group on here. So imagine we have this methyl group here. There's no strong electron withdrawing group to attract in the nucleophile to positions that are ortho and para with respect to that with electron withdrawing group. So what's going to happen here is the strong nucleophile is also going to be a strong base. If that's the case, which this one is a very strong base and also a very strong nucleophile, it can pick off a proton and leave a negative charge here. And so this negative charge would be in an sp2 orbital. And so since that's a relatively compact orbital, it's more compact than a p orbital or an sp3 orbital, that holds the electrons relatively close to the nucleus. Because the proton and the leaving group are not anti-periplanar, I can't do an E2 where the base would pick off the proton, swing electrons in, and push out the leaving group all in one step. So this is a pretty unstable intermediate with a negative on a carbon. It's not going to be as stable with a negative on a carbon as it is with a negative on a nitrogen. But at least over here, the negative was in a more elongated sp3 orbital versus the sp2. So that does help to stabilize that negative a little bit, even though it's not that stable for it to be on a carbon compared to a nitrogen. So once that forms, it's, as we said, it's quite unstable. It's going to shift in there and push out the leaving group to create something called a benzyne. And if this looks crazy to you, I'm in agreement. It's a crazy looking thing to try to form a triple bond in a six-membered ring, right? Because a triple bond should have a linear geometry. God, I can't write today. It should have a linear geometry due to the sp hybridization of that carbon. Right, an sp hybridized carbon has two sp orbitals 180 degrees apart from one another. So that's not working here because the sigma bonds there are not 180 degrees apart. These angles are more like 120. So these carbons really aren't going to take on the sp hybridization we would normally expect triple bonded carbons to have. So this is a really unusual situation. So if we examine the benzyne, it really doesn't behave like a triple bond, right? Because I can have p orbitals perpendicular to the plane of the ring overlapping to make a pi bond. That's what we normally have in an aromatic ring. But then I can't put another set of p orbitals perpendicular to that because that's where the ring is. And there'd be overlap there and steric hindrance there. So while the pi bonds exist from p orbital overlapping perpendicular to the plane of the ring, the triple bond there is it's going to exist more as if it's a pair of free radicals sitting in these sp2 orbitals side by side. And there's going to be a little bit of overlap there, but not a lot because they're not really aligned very well. And so these electrons are pretty unstable. It's not stable like a normal triple bond because the electrons are not getting effective orbital overlap in the sp2 orbitals that they exist in. But and also because because that third bond of the triple bond isn't really a standard pi bond, it's more like two sp2 orbitals with a single electron in each. It's actually really quite unstable. So it's very susceptible to any reaction. And so another molecule of the nucleophile could then attack and push electrons out. So we had our methyl group here to keep track of what's happening. So once the benzyne is formed, it's kind of symmetrical in that area. And so that means that the nucleophile can attack either of those two carbons of the triple bond. Whichever one it attacks, electrons will swing away to the other carbon to create a negative, again in an sp2 orbital. If it attacks this one, they'll swing up here and they'll exist here. And then the conjugate acid of the nucleophile will provide a proton to protonate whichever site ended up with the negative charge. And so in essence, I end up getting the nucleophile attacking the position that's para to the methyl group sometimes, and about half the time it attacks the position that's meta to the methyl group, because once the benzyne triple bond forms, there's no preference for the nucleophile really to attack one or the other. There's no sterics really blocking it or electronic positive charge attracting it to one side or the other once that benzyne forms. And if we look at this step, we might say, well, since this picks up a proton and regenerates an NH2, maybe the NH2 is acting as a catalyst. But really the answer here is no. A catalyst has to be regenerated in amounts that are equal to the amounts in which it was consumed. And in this particular case, if we go back and look at the full mechanism, one of the NH2 is consumed here when it picks up a proton. And then a second NH2 is consumed here when it attacks the ring. And then in this step, by picking up a proton, only one NH2 is regenerated. So if two NH2s are consumed and only one NH2 is regenerated, that's not a catalyst. We have to have an equal amount regenerated as was consumed for it to be a catalyst. Just want to point that out. Questions about that so far? All right. Further evidence for the existence of the benzyne. Right, so you take my word for it, or you could look at the experimental evidence that exists for its existence. Right, so without this benzyne intermediate, how do we explain about the 50-50 probability that the amide group will attack either of these carbons and give these two products in roughly equal amounts? I don't have any other, there's really no other explanation for why both of those would form. But if you're looking for more evidence in this reaction where the benzyne forms, if a diene is present, like furan or cyclopentadiene, those will undergo a Diels-Alder reaction to produce this product, which is observed as a product of the reaction. So that suggests that this is behaving like a pi bond that can undergo a cycloaddition or Diels-Alder reaction to do the cycloaddition product. So that's more evidence that the benzyne forms. All right, so here's a nice handy flow chart that helps you determine which mechanism is at play. When you have an aromatic ring, it doesn't have to be benzene. It could have things substituted on it. The question is, first question you want to ask is the reagent this benzene or aromatic ring with substituents, whatever they are, is what it's reacting with an electrophile or a nucleophile? And am I adding something like an NO2 that's really strongly electrophilic that I expect the ring to attack? If it's an electrophile, then I expect the EAS mechanism that we were discussing last week before spring break and on Monday. If the reagent is negatively charged, like an NH2 or an OH minus, those are obviously not electrophiles because they don't have a positive charge, they have a negative. And so if they're nucleophiles, then I'm looking at either the NAS reaction we talked about at the beginning or the elimination-addition reaction we just talked about that goes through the benzyne intermediate. So the question here is, when the nucleophile attacks the benzene ring, in order for this to occur, there has to be a leaving group somewhere. But then the next, so if you have a benzene ring with a leaving group and you add a nucleophile, you expect one of these two processes to occur. So then the next question you would ask yourself is, are all three criteria satisfied for the NAS reaction? Right, so just to remind ourselves, what were those three criteria? There has to be a leaving group on the ring. And there has to be an electron withdrawing group on the ring. And the leaving group has to be ortho or para to the electron withdrawing group. So really, you could summarize that as really one criteria. You have to have a leaving group and an electron withdrawing group, and they have to be ortho-para with respect to one another. If that's all true, then the first mechanism we talked about should be correct, and that'd be the mechanism that you would draw. If you have a leaving group and electron withdrawing group, but they're not ortho-para, then you would expect it to go through the benzyne intermediate. Or if you're missing the electron withdrawing group, the benzyne intermediate. So you've got to have a leaving group and a nucleophile to even get through this part of the flowchart. But once you're here, then the question becomes, is the leaving group ortho or para with respect to an electron withdrawing group? If so, then the mechanism is going to be the nucleophilic aromatic substitution one we discussed. If there's no electron withdrawing group or they're not ortho-para, then you go through the benzyne intermediate in your mechanism. So you definitely want to practice that up a little bit so you know which mechanism to apply if I ask you to draw it. All right, so now we have the ability to fill in all the blanks here. Now that we've talked about nucleophilic aromatic substitution, most of this flowchart question revolves around electrophilic aromatic substitution and reactions that occur at benzylic positions that we talked about before spring break and on Monday. And that is true for part A. So if I have an aromatic ring, there's obviously no leaving group here. So I can't really react a nucleophile here. The only thing I can do is react an electrophile to start attaching things to the ring. And what I'm noticing here is I want these two groups to end up meta with respect to one another, or 3 carbons away. So what I need to install first is a meta director and then install the second group. And I know bromine is an ortho-para director. This propyl group is also an ortho-para director, so I'm kind of stuck. So that prompts me to think, okay, since I know I can't install a primary alkyl group anyway, because of the rearrangement that occurs for a lot of the molecules, I'm going to set this up first as a acylation reaction that will convert the ring into a ketone. So that will install the 3 carbons I need, but it puts a CO double bond there. So the advantage of that is I know exactly which carbon the ring is going to attack, because when the chloride leaves, that carbon is stabilized through resonance, so that I don't have to worry about a rearrangement occurring. The ring will definitely attack that carbon and end up making a new connection there. The other advantage is having a CO double bond makes this a meta director. So it will direct the bromination to occur at the positions that are meta to it, which is what I'm looking for in this reaction sequence. So the second step there would be to do the bromination. That would install the bromine, so that step would then put the bromine on. But then I still need to now convert the CO double bond into a CH2. So I can use the zinc mercury amalgam with HCl, where the zinc provides the electrons, HCl provides the protons. To make this a water-leaving group, electrons come in, pick up protons, and become CHs. That's a 3-step process just to get from the benzene ring to this di-substituted benzene ring. So then I want to look at what step B involves. I can see the bromine is unchanged, but what's happening here is I'm going from 3 carbons to 1, and I'm oxidizing this. So if you recall, we said is if you have an aromatic ring and some alkyl group, as long as the benzyl carbon has at least 1 hydrogen, then the strong reducing agents like KMNO4 with a little heat, some NaOH, will be strong enough to cleave off the remaining carbons, the additional carbons, and oxidize this fully, removing the hydrogens all the way up to carboxylic acid. Since this involves OH minus, the OH minus would deprotonate that though. So if I want to put a proton on there, I need a second step where I'm using some H3O plus just to supply that proton. All right, so then we'll go back over here. If I do have this structure and I use nitration conditions, the nitric acid and sulfuric acid should form a nitronium ion. And then the ring will attack that. So then the question is, where will that nitronium ion end up getting positioned? So once this is an alkyl group, it's an ortho para director. So it should direct the ring to attack the nitro from the positions that are ortho and para with respect to that propyl group. And the bromine is also an ortho-para director. So it will direct the nitro group to come into the same positions, because those happen to be positions that are also ortho and para to the bromine. So I can definitely expect the nitro group not to end up here because of Sterics. We said last time that we don't expect an EAS reaction to occur on a carbon that's between 2 substituted carbons because of the Sterics. So then I'm considering here versus here. And again, Sterics is the major thing that's going to help me decide. So up here, the propyl group being fairly large is kind of blocking that collision that could occur. And so I expect most of the product to have the nitro group coming here. Since the bromine is just a single atom, it's not going to create that much sterics and block that out. So the product I would draw here would have the nitro group now connected at that position. If I then use these reduction conditions, that will reduce the nitro group to an amine. There's really nothing else on the structure that could be reduced, so I expect that to become an NH2 instead of an NO2. So all of that so far was stuff we talked about on Monday or before Monday. And the last step here is from today's content. So what am I seeing here? I'm seeing a strong electron withdrawing group that's ortho to a leaving group. So I should be able to replace that leaving group with the strong nucleophile. And what nucleophile do I want to bring in? Looks like I want to bring in ethoxide. So you could bring in a hydroxide and then deprotonate it and make the ether using the Williamson ether synthesis. So let's just show that, because I did see that in one group's answer and I thought that was an interesting way to set that up. So if you use hydroxide, like we just showed, to do this nucleophilic aromatic substitution reaction, the OH minus would attack here, push these electrons up to the carbon, they'd be stabilized through resonance as well as onto the oxygen, and then when they swing back in, they'd push the bromine out and you'd end up with an OH there. We'd need a little heat to overcome the activation energy barrier. Then we'd have an O minus here. Right, because if we used excess OH minus, it would also deprotonate the OH that would end up coming in or pushing out the bromine. So then we would just need to add like an ethyl bromide or something so that the negative charge on the oxygen could attack that ethyl group, push that bromine out, and then I get an ethoxide there. So alternatively, I could also just add ethoxide as my nucleophile. Right? There's nowhere else on the structure for the ethoxide to react, so it would just probably come in here, push electrons over here. They'd be stabilized through resonance, and then when they'd swing back down and push the bromine out, you just have an OET group there from that coming in. So there's a couple different options there, which would both be reasonable. Questions about that? All right, so that finishes up chapter 19. We're slowly getting closer to the end of the semester. So continuing along, we're going to start into chapter 20. Just to let you know, we got chapter 20, 21, 22, and 23, I believe. This is as far as we're going to get this semester, so we're definitely getting closer. So chapter 20 is about ketones and aldehydes. Ketones and aldehydes, as we've seen so far, are very common functional groups. There's a ton of ketones and aldehydes that exist in biologically relevant molecules, a ton of them in different pharmaceuticals. And we know that the CO double bond is a bit more stable than a CC double bond. So even though there are lots of alkenes, we know the alkene double bond isn't quite as stable as the carbonyl double bond. So that's a really common functional group. So here's just a few examples of some natural products that involve a CO double bond. A lot of these are in flavoring compounds. So vanilla, cinnamon, spearmint, almond, these flavors are sometimes used in food additives. Most steroids have a CO double bond group somewhere, just so you know. A steroid specifically is a class of compounds that usually includes these 4 rings fused together. Usually it's 3 6-membered rings fused to 1 5-membered ring, and then different groups might be positioned with different stereochemical positioning in space, and there might be an OH here or something instead of a CO double bond. There's a variety of different steroids, but many of them do involve CO double bonds. Those are the names of those compounds. So just like any new functional group that we haven't yet learned how to name by the IUPAC system, we want to talk about that for aldehydes and ketones. So aldehydes and ketones are named a little bit differently, but for the most part, we're just going to be continuing with the same IUPAC rules that we've already talked about. And the first step is always to identify and name the parent chain. So when you have an aldehyde, you have to make sure that the aldehyde carbon is part of the parent chain. So like if I have an aldehyde here, even though there's 8 carbons I could find that's the longest consecutive chain of carbons, that shouldn't be my parent chain because it's difficult to name this as a substituent. So instead, if that were there, I would want my parent chain to include that carbon and as many other carbons as possible, and then name the remaining carbons as a substituent. So find the longest chain that includes the CO double bond. Aldehydes and ketones, especially aldehydes, are a high priority group when it comes to numbering the parent chain. So I have to include this carbon in my parent chain, and I want to give it the lowest number possible. And so that means, since aldehydes are always on the end, an aldehyde functional group specifically requires a CO double bond with at least 1 hydrogen. So whatever else is here, this is always going to be on the end of the chain, because there's no way to continue the chain when there's a hydrogen there. And so that should pretty much always be carbon 1 when you're naming an aldehyde. So let's take a look at this as an example. It's got an aldehyde and a couple other functional groups. So I would find the longest parent chain that includes the aldehyde and start with that as being my first carbon. And I would number to make the longest chain I can. So that's 7. So my parent name should be heptanal. So the AL suffix. You got to be a little careful because depending on your handwriting, this could look like heptanol. An OL suffix indicates an alcohol, and AL suffix indicates an aldehyde. So in my parent chain, though, there's also an alkene. So it really shouldn't be heptane-al. It should be heptene-al. Right? The alkene needs to be indicated with an EN, E instead of an AN. So I really got heptene-al. I've got then a propyl, a 3-carbon chain here. It's a propyl, and that's on carbon 3 of the parent. So 3 propyl. And I've got an OH. So with the OH, I can name that as a substituent called a hydroxyl. And that's on carbon 7. So I got to put this all together. I got to alphabetize the substituents. So I should have 7 hydroxyl. 3 propyl. Hep. So my parent chain is heptene-al, But if I just write heptenal, I haven't included a number that tells me where the pi bond is. So I could put that here. So here the 4 indicates that the alkene is starting on 4 and bridging to carbon 5. And that the L at the end of that, the AL there, is indicating the aldehyde. And I don't need a number for that because if there's no number, it's presumed to be on carbon 1, which is pretty much where it should always be. All right, so that's for aldehydes. We'll take a look at some ketones. So the suffix for an aldehyde is Al. The suffix for a ketone is ONE or ON. And since a ketone is never going to be on the end of the chain, if it was on the end of the chain, then it would be an aldehyde. And it would be named with an Al suffix. A ketone is always going to be somewhere in the middle of the chain. So depending on where it is, we need a number to locate it. And that number can go before the parent name or can go before the ketone ONE suffix. So let's take a look at this one. So here we actually have 2 ketones. And we want to number our parent chain, giving the ketone the lowest number possible. And so that would involve starting here. 1, 2, 3, 4, 5, 6, 7, 8. We want to include all the substituents where possible. So this is now going to be a parent that's oct. For 8 carbons, I've got an alkene, so it's going to be octene. And now I've got 2 ketones, so it'll be called a dione. Octene dione. And I need a number here to tell me where the alkene is. And I need numbers here to tell me where the ketone or ON is, and that's on 2 and 6. So the parent chain there would be oct 3-ene 2,6-dione. And all of that accounts for the 8 carbons in the parent chain, the 2 CO double bonds, and the alkene. So what's not accounted for is the OH and the propyl. So here I have a 1-hydroxy and the propyl now is on 5-propyl. Oct 3-ene 2,6-dione. Any questions about any of those? So here was the quiz question then. I'm noticing that the quiz question has both an aldehyde and a ketone. So the aldehyde is going to take numbering priority. I'm going to number the parent chain from the aldehyde to give it the lowest number possible. And that gives me 7. So my parent is going to be hept. There's no alkene, so it's heptane. And I've got an aldehyde, so I would call it heptanal. So that accounts for the 7 carbons in the parent chain and the aldehyde. So then I have to name and number the other substituents, and I can treat the ketone as a substituent in this case. So there are really actually 2 ways to name this. So let's first talk about how to name the ketone as a substituent. As a substituent, the ketone would be an oxo group. So that would be 6-oxo. On carbon 4, I've got a cyclohexyl. And on carbon 3, there are two of them, so it's 3,3-dichloro. Oops, CHLORO. So if I put all that together alphabetically, comparing C versus O versus C, here CH versus CY, so that would be 3,3-dichloro for cyclohexyl, 6-oxo heptanal. I do notice at carbon 4 there's a chiral center, so I do need to determine whether that is R or S. So let's just draw separately over here what's happening at that site. So on carbon 4, there's a carbon that's 3, carbon 3. There's carbon 5. There's a hydrogen. And there's the cyclohexyl group, which is also a carbon. So the very first layer out, the best I can do is to prioritize the hydrogen as priority 4, which is always going to be priority 4. So I've got to compare these 3 carbons and prioritize them. Now, I can only go one layer at a time until I find a difference. So on carbon 3 over here, there's chlorines. The other carbons have carbons and hydrogens. So the chlorines at that very next layer are taking a priority with a higher atomic number than anything else. So this is going to be my top priority group because of the chlorines that are attached there. And there's also another carbon attached there. If I look at the other 2 groups that are attached here, my carbon has a carbon, carbon, hydrogen. Over here, it's a carbon, hydrogen, hydrogen. So this oxygen is not relevant because I've already found a difference between these groups. The 2 carbons cancel, but the next carbon takes priority over either one of these 2 hydrogens. So this would be priority 2, and this would be priority 3. And so when the 4th priority group is pointing away, and I go from 1 to 2 to 3 and it ends up being counterclockwise, that is an S configuration. So that would be one way to name that. Since the aldehyde and ketone both have their own suffixes, al and -one, I don't have to name the ketone as a substituent. I can also incorporate both suffixes into the parent name. So I could have the parent name be hept 6-one al. So I can put the 6-oxo if I'm naming it as a substituent in front of the parent name, or I could put the -one suffix and the al suffix both in the parent name, but I would need the 6 there to tell where the ketone is. I don't need a number in front of the aldehyde suffix because the aldehyde is always going to be on carbon 1. So then that would be S 3,3-dichloro for cyclohexyl hept 6-one al. So either of those would be an appropriate way to name that. So hopefully that gives you some practice naming. And if I ask you a question that involves naming an aldehyde or a ketone or a molecule that has both of those substituents, hopefully that practice will help you there. So next we want to talk about some reactions that will allow us to form aldehydes and ketones, and we've already seen a number. So here's just kind of a review of some reactions we saw last semester and this semester. Last semester we saw the ozonolysis reaction where you can make a ketone or aldehyde depending on whether there are groups or hydrogens on an alkene, right? Remember the alkene gets cleaved and replaced with CO double bonds. We also talked So that's these two are both ozonolysis reactions we talked about last semester. Last semester, we also talked about converting an alkyne into a ketone or an aldehyde, and that's through a hydration reaction. So if I do an anti-Marconi hydration using hydroboration conditions followed by oxidation, then the boron would end up going here, and the hydrogen would end up going there, and then eventually the boron would be replaced with an oxygen. So initially, well, if you recall last semester, we said this would produce something like this. Oops. That's an enol. Right? When I do a hydration reaction on an alkyne and I add a hydrogen and an OH across there, it produces an enol, and then that rearranges to produce the CO double bond because it's more stable than the CC double bond. So depending if I put the OH on the anti-Marconi position, that's where I get the CO double bond. Alternatively, if I do a Marconi addition using these conditions on an alkyne, then the OH ends up connected here and the hydrogen ends up connected there. So that OH again will be an enol and it will rearrange to produce through tautomerization the CO double bond at that position. So you want to keep those reactions in mind because they're especially useful synthetically. Earlier this semester, we talked about oxidation. We said we can convert a primary alcohol into an aldehyde using PCC oxidation conditions. We can convert a secondary alcohol into a ketone using the stronger oxidizing agent. We can also use the PCC here as well. PCC is also strong enough to convert an alcohol into a CO double bond. So that also works. And then more recently yet, we talked about the Friedel-Crafts acylation. So this is another way to produce a ketone specifically on an aromatic ring. So you want to practice those enough, drill them so that they're in your mind and you can use those for syntheses and solving problems. And so the next two quiz questions were really an application specifically of this reaction and this reaction. So if I ask you to start with, oh, actually, no, that's not true. This one is not. This one requires you to use the PCC. Right, so here, specifically, if I tell you to start with an alkyl halide, and I don't want to alter the number of carbons, I would obviously start with the ring there, and 2 carbons are connected, and then I would put my alkyl halide there, because so there's a couple different ways I can do this reaction. There's lots of different ways to do this actually, but probably the most straightforward way would be to use some NaOH, and if your quiz answer involves something different, I'll give you feedback on that, but the NaOH is going to give me the OH minus. As a nucleophile, that would come in, since this is a primary carbon, and push out the bromine through an SN2 reaction to give an OH there. And then I can oxidize the OH to the aldehyde using the PCC. So that's probably the most likely two-step process you would use to get that reaction to work. In the next quiz question, similar situation, we don't want to alter the number of carbons, so we'd start with the same number of carbons. If I'm expected to start with an alkyne, I need a triple bond here. And so that's 6 carbons in the ring and then 2 more outside, 6 carbons in the ring, 2 more outside. Don't just double check, we're not changing the number of carbons. So here I want to do an anti-Marconi addition. I've got an asymmetrical alkyne. On one side there's an R group, on the other side there's a hydrogen. And so if I do a Marconi competition, I'll add another hydrogen here and an OH here, and then that will produce a ketone, right? So just to point that out, if I use the sulfuric acid and the mercury sulfate, that's this one here. Oops, yeah, that would do the hydration Markovnikov style and add across one of the pi bonds an OH and a hydrogen. And then that would rearrange to produce a ketone. If I want the aldehyde, though, obviously I need to add the oxygen not to this carbon, but to this carbon. So I'm not doing a Markovnikov hydration, I'm doing an anti-Marconi hydration. So that would be using isoamyl borane or 9-BBN, some kind of borane reagent that only has one hydrogen, because the other two bonds that the boron has would be to R groups. That way this only adds across the one pi bond. And I wouldn't want to use BH3, which is the typical hydroboration reagent, because with the boron having multiple hydrogens, it could add across more than one pi bond. I only want to add across one pi bond. I want to keep the other pi bond so that I'll have the pi bond there in the form of the CO double bond. So that would be my first step, and then the second step would involve the oxidation and those are the conditions we need to replace the boron with an OH. So since this is anti-Markovnikov, initially the boron would go here. It would still have these two R groups connected to it, and the hydrogen would end up connecting here. So that's how I get an extra hydrogen here. Then the second step would replace the boron with an OH. So initially, that would give me this structure. I'd be adding OH where the boron is and adding a hydrogen to the other carbon. But then since this is an enol, I expect it to rearrange. CC double bond is not as stable as a CO double bond. And so that would be the final product after those two steps occur. All right, so that pretty much reviews and includes most of the reactions in which I would expect you to use to form a ketone or an aldehyde. So the next section of chapter 20 is about reactions that ketones and aldehydes undergo. And so the first thing we would do is to try to recognize whether a carbonyl, which is the general term that describes both ketones and aldehydes, or really any molecule as a CO double bond, is it a nucleophile or is it an electrophile? And when we look closely at it, we can see that these CO double bonds are pretty good electrophiles, right? What is an electrophile? An electrophile usually has some degree of positive, and it has the ability to accept a new pair of electrons, whether it can just accept them in like a carbocation, or maybe there's a leaving group that has to leave so the new electrons can come in. An electrophile has to be able to accept new electrons. What's nice about a carbonyl is that when a nucleophile attacks, it can push these electrons up to the oxygen, and a negative charge on an oxygen isn't terribly unstable. So even though there's no leaving group, and even though the carbon already has 4 bonds, it can still accept new electrons because the pi bond can break. If we think about the quantity of charge here, there's really a quite large partial positive on this carbon. And there's 2 reasons why that carbon carries a partial positive, and one is resonance. Right, so it's a minor but significant resonance contribution from this structure here. If the electrons, the pi electrons, which aren't held that tightly to the nucleus, shift up to the more electronegative atom. That creates a minor resonance contributor. It's minor because of the formal charges being relatively unstable, and so this, you'd imagine this shifting back in and going back over here. And so we recognize resonance is not a situation where it's shifting back and forth. In reality, the real structure would be the average of these two. But since this one's a lot more stable, the average would look more like that. So typically, if you're going to show the resonance hybrid for the CO double bond, it might look something like that, right? I don't really have a double bond. I don't really have a single bond. I have something that's almost a double bond because the double bond structure is more stable than the single bond since it doesn't have any formal charge. But there's going to be these partial charges that result from the minor contribution of this contributor to the average or hybrid. And so since there's a fair amount of positive here due to this resonance contributor, that makes it more likely for a nucleophile to be able to attack. And so that's the theme we're going to see moving forward with these reactions that carbonyl compounds undergo, is often the first step will be a nucleophilic attack. The other reason why there's a partial positive here has to do with induction. Right? So we know even if it wasn't for the resonance, oxygen is more electronegative than carbon, so the shared electrons should be pulled more in that direction, and that creates additional partial positive. So there's a lot of partial positive at this site that makes it electrophilic, both because of the resonance and the induction. And there's a third feature that these carbonyl compounds have that makes them electrophilic, and that is there's very little sterics around them. Because it's sp2 hybridized, that means it's flat, and the R groups are in this plane, but the nucleophile is going to come in and overlap with this p orbital that's perpendicular to the plane. So the trajectory of the nucleophile to attack this carbonyl carbon as an electrophilic site means that the nucleophile is going to come in almost 90 degrees, almost in a totally different plane from where all the sterics would be in the plane of the structure. Right? So it's not like the nucleophile, it's not coming in here. If it were coming in there, then sterics would be an issue because these big R groups are blocking out the approach into that plane. But that's not where we'd expect it to approach, because the nucleophile's orbital is going to come in here and form a new sigma bond, which is going to result from head-on orbital overlap between the nucleophile and the carbon. It's this p orbital that's going to rehybridize into an sp3 as the nucleophile's orbital comes in and overlaps with it. So the positioning of the attack, you can kind of think of that as occurring perpendicular to the plane where all the sterics is. And so the space above the molecule is pretty open since the R groups are in the plane. There's really not much to block that out. Now, if the R groups are extremely bulky, then they might block that out. And the more bulky they are, the more they would block it. But for the most part, it's pretty open. So since there's not much sterics in the trajectory of the nucleophilic attack, that makes this even more electrophilic. It makes it even more likely for a nucleophile to attack. So even though we don't have a leaving group, the nucleophile can attack here readily because there's a large quantity of partial positive there, and because when it does attack, there's not too much sterics, and the other electrons can shift out to the oxygen. So let's compare aldehydes versus ketones. So here we have a decent comparison. The difference is the aldehyde has has a proton directly connected to the carbonyl carbon versus a ketone. A ketone has R groups connected at both bonds to the carbonyl carbon. So how's that going to affect the electrophilic character of that carbonyl carbon? Right, so we want to look at all of the factors we just talked about. Probably the most obvious one is sterics, right? With the extra R group here blocking, they're really blocking the plane that they exist in, so they're not terribly blocking, the attack from the front or from behind on this flat structure. But they do create some more sterics, and these terbutyl groups especially are pretty sterically bulky, and they're three-dimensional, and they will block somewhat. So it would be more likely for a nucleophile to come in here and attack versus coming in over here and attack, because there's a little bit more sterics. And so that's generally true for ketones. So if we were asked which should be more reactive as an electrophile, aldehydes or ketones, the answer is aldehydes. And one reason for that is because there's less sterics. There's another reason. The aldehydes have more of a partial positive on the carbon, the carbonyl carbon. Right, so what we're talking about here is if I've got this carbonyl carbon, through induction, the oxygen's pulling electrons away. Also through resonance, it's pulling the electrons away, and that creates a lot of partial positive here. That's true for both aldehydes and ketones. But if I have an aldehyde and there's a hydrogen bonded there, the hydrogen doesn't have much electron density. All it has is this pair of electrons it's already sharing to help shift in there and balance out some of that positive. So there's still a lot of partial positive there. When I have a ketone, which is also shifting electrons up, creating a partial positive, if there's an R group here, that R group, which is going to be a carbon bonded to other things, there's more electrons. They can all shift in there through induction and push more electron density to diminish the size of the partial positive on that carbonyl carbon. So that makes it less electrophilic, less likely to attract an electrophile in if there isn't as much positive there to attract the negative charge of the nucleophile. So through induction and through hyperconjugation, because this single bond can rotate so that one of these R or hydrogen can bring its electron cloud in to kind of overlap with this p orbital here, and that shifts some electron density in there as well. So extra electron density from an R group through both induction and hyperconjugation can push electrons toward the carbonyl carbon, so it won't be carrying as great of a partial positive as it would if there were hydrogens attached. So because the hydrogen's less sterically hindering, and because it does not donate electrons through induction or hyperconjugation nearly as effectively as an R group would, I'm going to have a larger quantity of partial positive here, and it's going to be more likely for a nucleophile to attack there versus over here on the ketone. So aldehydes are especially electrophilic and lend themselves toward reactions with nucleophiles more than ketones do. All right, so let's look at some examples of some nucleophilic attacks on a carbonyl. So we've talked about a variety of nucleophiles throughout OChem 1 and OChem 2. So here's just one example, a halide. So this could represent iodide or bromide or chloride. We know the fluoride is not a good nucleophile because it's so well solvated. The solvent molecules form such strong attractions to it, it's not really free to attack very readily. But the other three, chloride, bromide, iodide, are great nucleophiles. So we could easily imagine the partial positive attracting one of these halides in there and pushing electrons up to produce this intermediate. The problem with that is the halide is also a great leaving group. Iodide, bromide, chloride, they're all great leaving groups. So once the negative exists on the oxygen, those electrons will readily shift back in and push that out, just to go back to where we started. So if the attack of the group as a nucleophile and the loss of the group as a leaving group can both occur, what's going to control this process is, am I getting this as my product or am I getting this, right? It's in equilibrium. Which side is equilibrium favored? Is it going to favor the attack or is it going to favor the loss of the leaving group? Both of those can happen readily. And so ultimately it comes down to which side is more stable or which side has more entropy. So the side over here, which is really the reactants, the initial reactants, is going to be favored by entropy because there's two molecules instead of one. It's also going to be favored by enthalpy because the negative is going to be a lot more stable on a halide than on the smaller oxygen atom. So what that means is not every nucleophile can just come in here without getting pushed back out. And if you have a halide is not a good nucleophile to attack a carbonyl carbon. Even though the carbonyl is nice and electrophilic, if the attacking group, because there's no leaving group and the electrons are still around, if the attacking group's also a good leaving group, they'll just swing back down in and push that leaving group out. So if I want to attack a carbonyl carbon with a nucleophile, the nucleophile can't also be a great leaving group. And so that means a hydride, a negatively charged carbon like a Grignard. A hydride would come from something like LAH. We've already seen those reactions. We know those can attack a carbonyl carbon and not get pushed back out because they're terrible leaving groups. A cyano group is also a bad leaving group, so that one should be able to attack and not get pushed back out. OH minus is a bad leaving group, but it's not terrible. So that one, if we imagine that attacking a carbonyl, I want to think about which side the equilibrium is going to favor. You can do that analysis. Which side is going to be favored? Well, the disadvantage here in this equilibrium is that the reactant side is always going to be favored by entropy because there's more molecules that can be positioned and moving around more with more variety than the product. And if I've got a negative on an oxygen on the reactant side and on the product side, they're similar in stability, but this negative would probably be more well solvated. There's no resonance or anything to stabilize it. So if there's no resonance to stabilize either side, the side, or induction really, or anything like that, the side that has a smaller grouping of atoms would be able to bring in solvent more to stabilize through solvation. So that really suggests that the reactant side should be pretty strongly favored. And obviously if water attacks, I would have an extra hydrogen here. And so this would be a situation where the neutral water and neutral carbonyl would have to come together, push electrons up, and form two charges at once. That's not going to be likely. That's really pretty unstable. So this is disfavored by entropy and disfavored by enthalpy because of the formal charges making it so unstable. So that would even go back even more. So that's the type of thing you want to be thinking about. If you have a decent nucleophile, but it's also an okay leaving group, you can think about it attacking, but the equilibrium is probably going to favor the reactant side. And with water, it's also going to favor the reactant side. But these three over here, they're going to be product favored. Right, so let me just mention one of those real quick. So if I've got a carbonyl and maybe the cyano group comes in, so initially the cyano group looks like this. There's a negative formal charge on a carbon, which is pretty unstable, but it's a compact sp orbital, and through induction the nitrogen's pulling electron density away to really help stabilize that, but still relatively unstable to have a negative on a carbon. So if that attacks, oops. let's try that correctly. I would get something like this. So now I have a situation where it's probably a bit more balanced in the equilibrium. So I've got two reactants on the reactant side, so that's favored in entropy compared to the products. But the products have a negative on an oxygen, which is a little bit more stable than a negative on a carbon. So the products are favored in that situation. So this could be more of an equilibrium. With the hydride and the Grignard or other negatively charged carbon, those are terrible leaving groups. If those come in, they're not going back out. Right? And we've seen those reactions, a Grignard reaction and LAH reaction. When those attack, electrons swing up, and that negative just stays until we add a proton source later on that it can pick up a proton from. So here's a key thing you want to think about. If the nucleophile that attacks is also a good leaving group, is it likely to react? No. It might react, but it's just going to get pushed back out, and the equilibrium is going to favor the reactants. And that's because of both entropy and enthalpy favoring the reactant side. And that's different from attacking an alkyl halide. Right, so we said over here, if an iodide attacks, then the oxygen is just going to swing the electrons back in and push it out. If I had instead an alkyl halide here, and the iodide attacked, since the leaving group's actually leaving, that could actually produce a product. I wouldn't necessarily expect that to go back unless the leaving group came back in, but that would require a new collision to occur. In this case, there's no new collision that really required to swing the electrons in and push that back out. I mean, there is a collision required, but it doesn't require. It's an intramolecular process, so it doesn't require something to come in and collide. It can do it when it bumps into anything, as long as there's a little bit of energy to push those in and push the leaving group out. So in order to do an addition across a carbonyl pi bond, like this, a ketone or an aldehyde, you have to have a strong nucleophile that is not an okay leaving group. It can't be pushed back out. And so that requires usually to be an R group or a hydride. And we'll see a couple other examples as we move forward and look at more detail. But the overall mechanism generically would be, if I have one of those strong nucleophiles that's not also a good leaving group, it would come in, push electrons up, create a negative, and then later when some product sources is added, the oxygen could pick up that proton. And so I would produce an alcohol from a carbonyl, right? And we saw that with LAH. We saw that with the Grignard reaction. So although ketones and aldehydes are good electrophiles, as we're saying, some nucleophiles aren't that strong. Maybe it only has a partial negative, partial positive. You know, like a water, for example. It's not easy to get water to attack here, as we were saying a minute ago, because if it does attack and pushes electrons up, I'm going to form some unstable partial charge, formal charges. A negative on the oxygen there, a positive on the water after it attacks. And so that would be likely to just swing back in and push that out and go back. So this is not a very likely process to occur. So there is a strategy you can use to make it more likely for a nucleophile to attack, and that is to make the carbonyl more electrophilic. How do I make it more electrophilic? Well, it's already electrophilic specifically because it's not very sterically hindered, and there's a major resonance and an induction that pulls electrons away from this carbonyl carbon. If we could make that more pronounced by making the electron shift even more toward the oxygen, it'd make this carbon even more positive, and that might attract even a weak nucleophile in there. Right? So that's the idea here. And the way to do that is to usually add a proton or an acid. By adding an acid, you can get the ketone or aldehyde to act as a base, right? So if I add HCl or sulfuric acid or something, H3O plus, something that's a strong acid, the carbonyl should pick up that proton and become protonated. And that makes the oxygen positively charged, so it really now is super strong at attracting electrons up from the carbon through both induction and through resonance, because now the other resonance contributor is not such a minor contributor. Both contributors have a formal positive, so they're both significant, and that means this contributor contributes more to the average or hybrid, creating more positive at the carbon to attract a nucleophile in there. So here's how that mechanism would look. So if you don't have an acid present, this is the mechanism you're looking at. You'd need a strong nucleophile to be able to attack and create a negative, and then that might pick up a proton. If you don't have a very strong nucleophile, so if this is weaker, you can add an acid first. Force the carbonyl to pick up a proton. Now it's really a very nice, strong electrophile, much stronger than it was initially with only a slight partial positive here. Now there's a really big partial positive at that carbon. So even a weak nucleophile can attack there, push electrons up, and make this product. You should keep in mind, though, that you can't do both. You can't use both an acid and have a strong nucleophile. Maybe with a couple exceptions, but generally you can't do that, because if I have a strong nucleophile, it's probably also likely to be a strong base, which means instead of attacking, it would probably just pick off the proton and go back. So this specific strategy of using an acid to protonate a carbonyl and make it more electrophilic is usually only used when I have a weak nucleophile, something that's also a very weak base, something that's not likely to pick off the proton, but more likely to attack to produce an addition product. So this is nucleophilic addition, adding across the pi bond a proton to the oxygen and some nucleophile to the carbon. And so those are the general strategies there. And next Monday, when we continue chapter 20, we will focus on more strategies for looking at some specific examples, more specific examples of nucleophiles attacking carbonyls and the reactions and variety involved in that. So in the meantime, try to practice up from the stuff we just talked about. Let me know if you have any questions about the examples or the bullet points. And then, just keep rolling here and get closer to the end of the semester. So please reach out anytime.